Good morning. We're about to get going here. So I want to sort of make sure we are familiar with where we have come from for the last couple of lectures so that we know where we are going for today's lecture. So I think we began our discussion of AC analysis by going over a review of complex numbers. And one of the things that we saw with complex numbers is that we could represent those complex numbers graphically. We could represent them as vectors on the complex plane. So that's going to be an important point that we come to today at some point. Then you saw a lecture where we could convert circuit components, particularly inductors and capacitors. We could convert those maybe inductance or capacitance values to these things that are called complex impedances. And so that's actually what I have sort of near the bottom of this page right here are some formulas that we have that we can use to basically turn a capacitance value in this bottom one into a complex impedance or turn an inductance value into a complex impedance, right? So that's one of the other pieces that we have gotten to see so far. And then the last piece is that we can express the voltages and currents that may be flowing in a circuit with these values that we call phasors, right? And phasor values are basically values that they are complex numbers, which they are expressed so that you have like a magnitude and an angle that comes along with it. That kind of goes along with how complex numbers get expressed graphically. But those two values represent specific things because when we're dealing with single frequency, steady state AC problems, then the sinusoidal, I should say as well, sinusoidal AC problems, the thing that matters to us in those kinds of cases is essentially really nothing to do with time. The things that matter to us have to do with the amplitude of the wave and the phase shifts of the wave. Okay, so we're basically able to represent those two pieces of information with phasor values without sort of having to take the rest of the information that would end up making it way more complicated. We can get cut right to the chase and express just the values that matter to us with respect to these waves. And just to kind of give it a little bit more I guess, bring it down home just a little bit better. What I thought I would do is go ahead and review a couple of things that sort of matter to us with respect to expressing phasors. What if we have sources that are expressed instead of as these frequency domain phasors? By the way, that the piece of phraseology that says frequency domain, that basically is somewhat synonymous with the idea of phasors, right? Frequency domain, phasors is how you express something in frequency domain. Anyway, with these expressions that I have right here, these are in time domain. And we need to be able to convert expressions of essentially time domain where there's like this wave that you can maybe trace out relative to t. We need to be able to convert these into phasor values. So this first one shouldn't be too hard for any of you. How would you convert that first one? 5 volts, right? Angle of 65 degrees. So the big point there is that when you have one of these time domain expressions that is given in terms of a cosine function, you can pull over whatever that phase shift value is, you can bring it directly over and make it the angle value of your phasor. Okay? Now, what about this next one down here? Now, this one's showing you a current source. That doesn't really matter so much. The question I have for that current source is, do you do the same thing? Almost the same thing. That's a good answer. Okay, what has to change? Okay, we need to convert this sine function into a cosine function, and the way you do that is you basically subtract 90 degrees from whatever you have there. So what that gives you is 5 amps at an angle of what? Negative 25 degrees, right? All we did there is we subtracted 90 degrees from 65 degrees, and that gives you negative 25 degrees right there. Okay, the other thing that I want to show you here is that the phasor values that we come up with in terms of voltages and currents, those actually sort of work with our complex impedance values the same way that voltages and currents work with resistance values when we are dealing with DC circuits. All right, works basically the same way. The only difference is we are now dealing with complex numbers instead of just plain real numbers. So with a problem like this over here, I'll just kind of pick off a few kind of characteristics of it. We have 10 volts at an angle of 20 degrees, but it's going through a series of two resistors that have the same value. What do you think would happen as far as the voltages that would exist across either of these two resistors? The fact that they have the same value would tell you they should be dropping the same voltage, right? And it's not when we express things as phasors, it's not limited to doing things with sources. We can also express voltages anywhere in a circuit with phasors. This is one of the ways that I figured I would show you this. If this is 10 volts angle 20 degrees, then the voltage across this resistor is probably going to be 5 volts angle of 20 degrees. Okay, and then what about across this one? Again, 5 volts at an angle of 20 degrees. Okay. The reason those angles didn't change is that there really isn't any kind of a phase shift that happens with resistors for either voltage or current, right? Voltage, now in this case, we wouldn't necessarily expect there to be a phase shift anyway because we're dealing with voltage and voltage. But the other thing I can do is I can say, well, what would the current be in this little circuit, this little sample circuit? How would you come up with that? Let's say the current would be something like this. I could call it I. How would I express I? Okay, V over impedance, right? The voltage over the impedance. And so what you would have there is basically 10 volts angle of 20 degrees divided by what? 10 ohms. That would be the overall resistance of that whole circuit. And so what would that give you? 1 amp at an angle of 20 degrees. Okay, now this was because those were resistors, right? If we had had something that was either a capacitor or an inductor in this circuit, there's a possibility we could have ended up with a different phase value over here for the current than we did for the voltage. And so we're going to see some examples of how that works as we go through our circuit analysis techniques that I'm going to show you today. Okay? The last little note that I want to make is that when we are combining complex impedances, they combine the same way as plain resistors do in DC circuits. Okay? Meaning, if you have two complex impedances in series with one another, they just add. If you have two complex impedances in parallel with each other, or two or more, I should say, they combine similarly to how resistors combine when they are in parallel, right? Reciprocal of the sum of the reciprocals, or if you just have two of them, you can do the product over the sum technique that we've seen several times. Okay, so that's kind of some review stuff that I wanted to go over. Now let me actually really boil it down for you and show you the steps that I recommend when we're trying to approach a steady state AC problem where the waveforms are sinusoidal. Okay, single frequency, that's the other factor that I should probably mention here as well. First thing you want to do is take all of your sources that you have in your circuits, and if they are not already expressed in frequency domain as phasors, you want to convert them to that. Okay, a couple of notes as you do that. Make sure you watch for sine functions, right? Your friend is cosine functions, because then you can just directly convert over whatever your phase angle is from your cosine expression to your phasor value. But if you have any sine expressions, you want to make sure you subtract 90 degrees like we did just a couple seconds ago. Okay? The other thing that I'll mention here about phasors is that if we're really technical, we don't want phasors to have negative values. All right, what you're supposed to do instead, if you end up with a phasor that has a quote-unquote negative value, that really represents vectorially a vector that points 180 degrees away from the one that you maybe we're trying to say, right? So if you had something that was at an angle of 10 degrees, but with a negative magnitude, that would be the same thing as basically 190 degrees, because you basically have to shift by 180 degrees away from where it was pointing, okay? Second thing, for anything that you have in your circuit that is not already expressed as a complex impedance, so this is for your passive elements in your circuit. If you have any passive elements in your circuit that are not already expressed in terms of complex impedances, you have to convert those to complex impedances, okay? Remember that when you do that, you have to know what angular frequency you are driving the circuit at, okay? So that's kind of an important point. You'll need to know that omega value, and you need to have that omega value expressed as an angular frequency, and the way that we do that is we express it in radians per second, okay? And then we use those formulas. ZL is equal to j omega L, and ZC is equal to minus j over omega C, right, for inductors or capacitors. Those are the two main elements that we think about that would need to be dealt with according to one of these complex impedance formulas. Once you have expressed all your sources and your passive elements as these complex values, there really isn't anything more for you to do besides go through and do a circuit analysis using any of the techniques that we've learned so far for DC circuits, but now the values that you are going to be operating on are complex values as opposed to being just plain real values. So all of the lists that you might be familiar with, right, doing equivalent resistances or doing voltage or current division or practical source transformation or superposition or nodal or mesh, Thevenin and Norton, right? Any of these techniques that we have used for DC come over to AC as long as we understand that we are operating on complex values as opposed to real values, okay? So hopefully you're good and solid on all those concepts so that, now that we step forward and apply them to complex numbers, you're okay with that. Sometimes, this isn't always important, it depends on what the question is asking for, but sometimes there's a step 4 where the problem wants you to convert whatever your results are that are going to come out as phasors, right? Let's say you've solved a bunch of stuff and you come up with some voltages or currents. Those are naturally going to come out as phasors when you're using these complex numbers to do your analysis, right? Occasionally, your problem might ask you to express those results in time domain as opposed to frequency domain. That's not that big a deal because all you have to do is do the opposite of how you would have converted a cosine-based time domain function into a phasor. You just have to go the other way, right? And take the phase angle and apply it to a cosine-based function, okay? But that's a big thing, is make sure when you do that, you don't use a sine function. You do want to use a cosine function when you do that, okay? So those are the steps. And so this is one of those pages that you might want to sort of, if not formally, somewhat informally commit some of this to memory, because this is what you're going to use every time you go about trying to solve a AC problem, okay? So that's actually what we're going to do right now. We're going to solve an example problem. All right? Here's the example problem that we are going to try to solve. Okay, with this one, we have a voltage source over here on the left that is given as 40 volts sine of omega t plus 80 degrees. Okay. Separately over here in the problem statement, it says that that voltage source drives this circuit at 300 hertz. Okay, the word hertz has a particular meaning. What does that word hertz mean? That means cycles per second, and so it's going to be important for us in just a few minutes to make sure we convert that properly to an angular frequency as opposed to sort of this cycles per second type of a frequency. Okay, so I'll mention that right now. Then this voltage source drives a bunch of circuit components over here in this little circuit. Okay, and we are asked to basically perform several steps here. And as we perform these steps, we're going to hopefully end up with a better understanding of how voltages are applied across the different circuit elements that are in this circuit, as well as how currents are going to be flowing through the different circuit elements in this circuit. Okay, so that's kind of what we're heading after with this problem. Okay, so toward that end, let me kind of reiterate, you're really going to want to probably have your calculator out and ready to go on this problem, because we are going to use we're going to heavily use the calculator's functionality to solve this problem. Okay, so let me start with part A down here. Okay, part A says we need to find the complex impedances for each set of passive components connected in series. Okay, so where do we see sets of passive components connected in series? Yeah, so I think what some of y'all are getting at, if you look at this little circuit right here, one of the things we can do is we can go in here and actually convert some of these strings of components and try to come up with what an equivalent complex impedance is going to be for that set of components. And so what I'm going to do is go ahead and replace those like this, where we say this is going to be, I'm going to use the letter Z sub S, okay, for that little string of 3 circuit components that are all in series with one another. What do you think I'm going to do with these circuit components down here? What I'll probably want to do is name these something. I tell you what I'll do is I'll name this one Z1 right here, and then I'll name this one over here Z2. Okay, so what part A of this problem is asking you to do is to basically go in here and come up with complex numbers that represent the complex impedances that are essentially seen in each of these boxes, because each of those boxes represents a set of impedances that were in series with one another, or passive components that were in series with one another. Okay. While I'm here, let me do one other thing that the problem doesn't ask me to do, but I think it might be good for me to go ahead and do it right now. In our circuit analysis steps that I listed for you just a few seconds ago, one of the things I said you should do is convert any time domain sources into frequency domain by expressing them as phasors. Okay? Do I have any of those that I should do on this problem? Okay? 40 volts sine of omega t plus 80 degrees, how should I convert that? 40 volts at an angle of 80 degrees minus 90 degrees, right? So this would be 40 volts at an angle of minus 10 degrees, right? That's how you would convert from the originally stated source that I had up there and convert that into what that should be as a phasor. Okay? So there is a kind of a nicely converted circuit right there, and it's ready in terms of the phasor expression of the source right there. It's ready as far as that's concerned. Now what we need to do is go in and find what these complex impedance values are going to be. How should we start with that? Okay, so someone says maybe we should convert our 300 hertz first, and I think that's not a bad way to start, because one of the things we're going to need in order to find all of these complex impedances is an omega value, right? So what is omega going to be? Well, it is going to be related to our hertz-based frequency, our cycles per second frequency, right? But it's not going to be exactly that, because in one cycle, right, it's like a full circle, how many radians do you have? 2 pi, right? So if we take 300 hertz, which is 300 cycles per second, and we multiply this by 2 pi radians per cycle, that ends up giving us a angular frequency value. Okay, so let me go ahead and get that in here. Here's the calculator. We've got 300 times 2 times pi. Okay, and it says 600 pi. If we want to see that without the pi in there, that ends up being 1,884.96. Okay, this is going to be in radians per second. And I said I'm going to really use this calculator to its fullest extent. What I'm going to do right now with this number is I'm going to store it into variable A. And one of the things that I do when I'm planning on using a lot of calculator storage in my solutions is I note in my hand-based solution here, a lot of times I even do it in a different color, I note what I have stored that value into in the calculator. So I'm going to say that value right there is stored into variable A in my calculator. Okay? What's next? Okay, we need to go in and find these complex impedance values, but you'll notice there, for ZS, one of the things I might want to do first is figure out what these complex impedances are individually for my inductor as well as for my capacitor up there, right? So how would I do that? For the inductor, what would the formula be? It's going to be J omega L. What's omega? Okay, it's in A. I'll write it one time like this, but I may at some point revert to start writing the letter A because I know I've got it stored in there, okay? So J omega, and then what's the L value? What I'm dealing with is this one up on top, so it's going to be 0.1, right? Millihenry means 10 to the minus third henries, right? So I'm going to say 0.1 times 10 to the minus third. What's a henry? Ohm seconds, okay? So this would be in ohm seconds. That's what a henry is defined as. Okay, so there is that expression, and if I go ahead and punch it in the calculator, what I will have is I times what I have stored in A times 0.1 times 10 to the minus third. And what that gives me is 0.188496. And I missed something as I wrote that down. What did I miss? J, right? That's going to have J in it because it's an inductor, right? And then I missed something else too. What else should I have on there? You'll notice here that the seconds divided out. Radians is technically unitless, so I just have ohms left. Okay? And so what I'm going to do with that is I am going to store that for now into variable B. Okay? What's next, you think? Maybe I want to convert that capacitor, and that capacitor up there is 1 millifarad. To do that, what I want to do is, again, take that angular frequency. This time I will just, you've seen, I can either write the number down or I can say, hey, I've stored that into such and such a variable. So I'm going to go with that strategy, right? Minus J over omega C, where omega is stored in A. And what's my C value? Okay, 1 millifarad. 1 millifarad is 1 times 10 to the minus third. And what's a farad? Seconds per ohm, right? Now, it's a good idea here at this point, because I didn't write down my number with units over there for A. What units do I have in A? Radians per second. What you'll see happen there is that the seconds will divide out the seconds that were in A, right? And you'll end up with 1 over ohms, but that's in the denominator. So that gives you just ohms in terms of the units that come out of an expression like this. So what this ends up giving us then, let me punch it in. What it ends up giving us is negative I over, okay, down here I'm going to put in A times 1 times 10 to the minus 3. All right, and I'll hit equals. So we have negative 0.5305 J, right? Or the way we would normally write that is negative J 0.5305 ohms, right? What do you think I'm going to do with that one? Why don't I store that in C? So that was for the capacitor. I didn't label it, but that was for the capacitor. Now what? Okay, those were for the two elements up here on the top that we needed to convert. What about the 2 ohms? Okay, That one doesn't need conversion. Resistors don't need conversion to complex impedance because they are already in a form that's appropriate for complex impedances. So I don't need to do anything to convert the resistor. What do I need to do? I probably need to add up those 3 complex impedances that I now have, 2 ohms, and then these other 2 that I just found. I need to add those up to get what my overall complex impedance is on that little leg of the circuit up there. Okay? So that's what I'll do. I will say ZS is going to be equal to 2 ohms plus B plus C. Right? So I'm going to go ahead and put that in here with 2 plus B plus C. All right? And that ends up giving me 2 minus 0.342 J, or I should say that in our kind of standard notation that we use. A lot of times what I will do is then put the ohms after an expression like this, and that is ZS. I'll tell you what I'm going to do just to kind of try to make this clear. I'm going to put a colored box around this and say that is the complex impedance for that little element that we've converted up there. Okay? Do you think I might need this later? Yeah, I think there's a pretty decent chance I'm going to need that later, so I'm going to store it into variable D. Okay? And I'm going to make a note of that right here. All right. So we've done one of our little sets of series complex impedance, conversions that we have to do. What do we want to do next? The next ones, right? With Z1, right? What's involved in Z1? 3 ohms plus the 1 millihenry value right there. So, yeah, we should be able to do that one relatively easy. Tell you what, I'll even do it in one step, right? Z1 is going to be equal to 3 ohms plus what? J omega, right? Omega's in A. What else? L, which would be 1 millihenry, right? And that would be 1 times 10 to the minus third ohm seconds. And again, the seconds is going to divide out with the A value over there because it's in radians per second, and you'll just end up with ohms. So what I'll do there is I will take 3 plus I times A times 10 to the minus third. Okay, that gives me, let me express it this way, 3 plus 1.885, we'll say. And that would be times J, right? So I'm going to put J over here, like this. Ohms. Do you think this is something I might want to keep? Probably so. Let me store that in E. Okay. I don't know, the next color in my little list right here is green, so I might highlight it green. Okay, that's this guy right here. All right. What's next, do you think? How about Z2, right? Z2 is a capacitor, though, and to deal with this one, it is a capacitor that's in series with a resistor, right? So I am going to add the 9 ohms to whatever the complex impedance is for that capacitor, right? So I'm going to say that down here like this. 9 ohms plus, it's a 100 microfarad capacitor, right? Right? Yeah, so minus J over, down there I'll again use that variable A that I have stored, that's the omega value, and then 100 times 10 to the minus 6, that's a micro, right? Is 10 to the minus 6. What are the units for a farad? Seconds per ohm. You'll notice again the seconds will divide out in the radians per second that's in variable A. So that part's no problem. This one also winds up giving you ohms out of that fraction term right there. So let me go ahead and put this in. We'll take 9 plus, here I'm going to have minus I divided by A times 100 times 10 to the minus 6. This gives me 9 minus 5.3, we'll just leave it with that, 9 minus 5.3 J ohms. And again, you think that might be an important value for us? I'm going to keep that one in F. Okay, and because we were color coding some other things, let me color code this one also. That is this impedance that we have right over there. All right, I think that may take care of everything that was asked for in part A. It said, find the complex impedances of each set of passive components connected in series. All right, what does it ask for next here? We need to know what this current is that's supplied by the source, and it asks us specifically to give that to them in time domain. Okay, we can do that. What do we want to do with this circuit now? Yeah, I think doing one more combination of complex impedances might be in order to turn this into essentially just a big series circuit, right? Just one series circuit. What I mean by that is, let me take this circuit right here and copy it, put it down here. And what we're going to be trying to do here is to convert that for part B. Part B is where we're trying to find IS, basically. We're going to convert this circuit into one where we replace all of that stuff, and maybe we'll replace this right here as well with a different value. Let me call this ZEQ1 maybe. Okay, now once I've done that, this current that flows through that leg is no longer I1. Why not? Okay, I collapsed two different current paths into one when I did that equivalent right there, so that number I should probably erase there because it doesn't exist anymore in this equivalent circuit. Okay, now what about VZ? That one does still exist because it's still across the same two nodes. Right? Those two nodes didn't go away when we collapsed that into an equivalent inductance there. So there is the circuit that I'm going to work with, and we're trying to find IS. Right? What do you think might be helpful for us to find IS? How about ZEQ1? How do I find ZEQ1? Okay. You'll notice that the two things I collapsed were basically this value I have stored in E that was in parallel with the value that I have stored in F, right? Z1 was in parallel with Z2. We collapsed those down. And so what we need to essentially do there is take the value that I have in E, multiply it by the value I have in F, and divide by the value I have in E added to the value I have in F, right? That's how we come up with an equivalent resistance as we take the product over the sum. We're doing the same thing here, and we happen to have those values stored into our variables. So that says ZEQ1 is going to be now equal to E times F divided by E plus F. Okay, now this is going to spit this answer to us out in rectangular form, and I'm going to keep it this time, and I'm going to share something with you. For me personally, when I see impedances, my default that I like to see those in terms of the format is rectangular form. Why do you think that might be? Okay, well, he says it's because that's the way the calculator gives it to you. Not quite. It allows me to automatically have separated a resistive part with essentially the part that comes from inductors and capacitors, right? So it sort of naturally means something to me when it's in rectangular form, and so I typically leave them in rectangular form when I'm dealing with impedances. Having said that, it's not wrong for me to convert it to a polar form, right? That's not wrong for it to be in that form. I just prefer to leave it in a rectangular form when it's an impedance because it seems like it has a little bit more meaning for me personally. That's a personal preference thing, but I figured I'd share it with you. So let me write this down. 2.83, I'll just say, 2.83. And then it says plus 0.894, and that's with a J with it. And what are the units on that? Ohms. And do you think this is going to be an important value for us? Okay, I think so. But we're kind of running out of some variables. We're using up our variables real fast. If we could use x and y, we also can use m. There's actually 3 more that I have to use, but I might want to use some of those later. If you think about your problem like this and you maybe start running out of memory space, it's a good idea sometimes to go back up and say, is there anything up here that I'm not going to need again? Yeah, B and C right here have served their purpose for me. Okay, so I am going to overwrite B. Okay, and then some people might choose to like put a little note right there or something, say, hey, I just overwrote that value, right? All right, so let me put that in B. Okay, what next? What were we trying to find? IS. Is there a need to do much more analysis before we go to try to find IS? Probably not, because we now have these 2 complex impedances that are in series. And it's just a plain old series circuit, just one loop, right? Because it's just a plain old series circuit, I would say it looks like it's possible for us to find IS by taking the voltage that's being applied and dividing by what? The equivalent complex impedance from these 2, which is just the sum of them, right? So we're going to have 40 volts at an angle of minus 10 degrees divided by what? What was ZS? ZS is stored, if we look up here a little ways, ZS was stored into variable D. And then ZEQ1 we just stored into B. Right? And what we're doing there is we're taking the amount of voltage applied to this series circuit and we're just dividing by what that equivalent impedance is, which is just the sum of these 2 impedances in series. Right? So let's do that. I don't think I have 40 volts angle of minus 10 degrees stored anywhere, so I'm going to have to put that one in manually. So 40 at an angle of negative 10. At this point, it's probably a good idea for me to just double check that my calculator is in degree mode, right? That's kind of a big deal. Make sure that you're not mixing modes there. And then I'm going to take this and divide it by D plus B. Now, I said a second ago that I like to see, these complex impedance values, I like to see those in rectangular form. When I see voltages and currents, how do you think I like to see those? I like to see those in polar form. Why do you think that might be? It has more physical meaning to me, right? The amplitude value in polar form is the size of the wave, right? And then the angle value is how far that wave has shifted relative to 0 angle, right? So it's how far is it shifted, and you can kind of use that relative to your other values to know how the waves might set up next to each other, right, in terms of time. Okay, so what I'm going to do with this one then is I'm going to convert it. In the complex menu, there's an option there. It says to R angle theta, right? That has a little arrow there that says convert that to polar. So I'm going to do that one right there, convert that to polar, and that gives me 8.23 units. I just took volts and divided by ohms. That should be amps, right? 8.23 amps. Angle of what? Okay, negative 16.5 or so degrees. Okay. And that is what that part of the problem, it's actually close to what that part of the problem was asking for. What did it technically ask for up there? It says expressed in time domain. How do I take that and express it in time domain? What I need to do is say, I'm going to put lowercase I of s here. This is not necessarily uniform notation that gets used everywhere, but in a lot of places, using a capital means that you are in this frequency domain, and using a lowercase means that you are in time domain. So again, that's not always done that way necessarily, but I'm going to use that as a way to notate this. This is going to be equal to 8.23 amps cosine of what? Yeah, so we have that angular frequency value that we came up with a few minutes ago that was around 1884, I think, 0.9 or something like that. This is in radians per second, T, then what? Okay, minus 16.5 degrees. And it is totally fine if you mix angular units in an expression like this, okay, as long as you label them, right? You want to make sure you are labeling the things in there. I will say, if you do not label it at all, you don't put any unit next to something that kind of refers to an angle, what is the default? Radians, okay? So I like to explicitly label them, either way. But, if you leave it unlabeled, the presumption is it's radians, okay? All right, so that is what that part of the question was asking for. Let's look at what else it wants us to do. It says, find currents I1 and I2 that are flowing through these two legs right here. So with the equivalent circuit that I drew just a second ago, I eliminated I1 and I2, right? What's a good idea now, maybe? I probably want to bring it back, and to do that, let me copy the version of this circuit that still has those legs in it, right? And I'm going to put it right down here. Still has those legs in it. Let me do another thing too while I'm here. I believe ZS, we just used that, and that value is stored in variable D. So I'm just going to note that right here. What are some of my other values? Z1 was stored in where? E. So I'm going to put that to the side of that one. Z2, I believe, was in F. Okay. And then IS, that's another one that I have recently stored, right? Or did I store it? I don't know that I have stored it yet. That's actually, I think it's still sitting on my screen here, so it's probably a good idea to store it. Where should I store it? Totally fine with me to store that into C, because C is another variable that I don't think I'm going to need again, right? Okay. So let me label this down here and say IS is just going to be equal to 8.23 amps at an angle of negative 16.5 degrees. And I will note there that that was stored into C. All right. And this, what we're dealing with here, I believe, was part C of the problem. Where should I go now from here? Okay. Current division, exactly, right? This in a DC circuit, if we knew this IS current that comes up through ZS and then splits into I1 and I2, right? We would just say, let's use current division. And this is no different. We can use current division here also, okay? So what that looks like here is that I1, let's say, is going to be equal to IS multiplied by what? Probably Z2 over Z1 plus Z2. That's what we're essentially trying to do. In terms of doing it with our calculator, what would maybe be another way to state this? C times F over E plus F, right? So let's do that. C times F divided by E plus F. Okay? And this is a current, right? We're trying to solve for a current. What did I say my preference is to see currents in? Okay. I like to see those in polar form. And so that gives me 6.89 amps at an angle of negative 31.1 degrees. Yeah, so do you think this is is this an important value to us, you think? Probably so. And at this point, I don't know of any of my other variables that I'm necessarily willing to let go of. So what do you think I might delve into here? I'm going to go to M. Yeah. We're going to put this in M, right over there, M. Okay. What if I want I2? You could switch subscripts and do another current division where the only thing that you change is you put Z1 up here instead of Z2. Or you could say I2 is just IS minus I1, which might be just a couple fewer keystrokes perhaps, all right? So what this is going to just be here is C minus M, right? So let me do that. C minus M. All right, let me put that in there. And this is also a current, right? So I'm going to convert it to polar. 2.337 amps at an angle of 31.5 degrees. Now, I'm not 100% sure if I'm going to need that again or not, and because I'm not sure, better safe than sorry, let me put that into Y. Now, yeah, good question just came up. Did the problem ask for those in time domain? Let's go look. Expressed in frequency domain. It is probably more common to see these AC problems say, hey, it's fine to leave it in frequency domain. You just need to know how to do the conversion to time domain if it asks for it. Okay? All right, what's the next part of the problem? Voltages VZS and VZ expressed in frequency domain. Okay? Good news on that is we can essentially just use, quote unquote, Ohm's law. I put it in quote unquote. Why do I say that? Yeah, Ohm's law is a little bit more specific, but this works the same way. It's essentially the same principle as Ohm's law, where you can get the relationship between voltages and currents for a particular element the same way that you have with voltage, current, and resistance in DC. Okay? So here's what that might look like. All right? Let's say I want to know VZS. Okay? VZS is just going to be equal to IS times IS times ZS. Okay? Do I have those stored? C and D. Okay? What kind of a quantity is this? It's a voltage, and so I probably want that in polar form. That's just my preference. So I'm going to convert that to polar form like this, 16.7 or so volts at an angle of negative 26.2 degrees. Okay. I actually am going to store this one. I'm going to store it into X. And then what next? Okay, it says voltages Vs and Vz expressed in frequency domain. Vz is the same voltage across either the left leg over here or the right leg. So I can pick one, right? I could either pick one and find the current through that leg, multiply it by the impedance of that leg, and that gives me the voltage across that leg. So that's one way to do it. What's another way to do it? This is actually a voltage loop, right? So VZ plus VZS had better equal 40 volts angle of negative 10 degrees, right? That might be the easiest way to do it of all, right? I don't know. I'm just saying there's multiple ways we can attack it. Let me show you that one. VZ is going to be equal to 40 volts angle of minus 10 degrees minus 16.7 volts angle of negative 26.2 degrees, which we have stored in X. So what I will do there is just punch that in, 40 angle minus 10. I don't know if it's important or not, but I sometimes put parentheses around here just to make sure I'm collecting things right, minus X. This gives me 24.4 volts at an angle of about 1.02 or so degrees. And that was the last thing for me to find, so I don't think I need to store that variable anywhere. Now, you might think we're done with the problem, and we're pretty close to being done with the problem. but I have a special treat for you. You know, you tell your kids you have a special treat for them, you know, this may not be what they think of, what I'm about to show you, but we'll see, you know, maybe. Would you say that for this little circuit, as a matter of fact, let me copy this circuit real quick. For this circuit right here, would it be possible for us to plot the results that we just got? Say, plot them on a complex plane or something. Okay. And I took the liberty of doing this so that you could see a couple of things. During the course of our solution for this problem, we used a couple of sums. One of them was a voltage loop sum, and one of them was a KCL kind of sum, right? How do those sums look on this set of complex axes? Okay, we'll start with the current over here. I1 plus I2 was equal to IS, right? How does that look like on the complex plane? See how when you add the I1 and the I2, you add those together, you get your IS. Right? Isn't that kind of cool? All right. We also had that if you added VZ and VZS, you would end up with the source voltage. Right? So here is VZ up here on the top. VZS was down here, right? Add those together, you end up getting your source voltage. Now, this might not still mean a whole lot to you when you look at it like this. You go, okay, that's how complex numbers work. Great. I'm going to make it mean just a little bit more to you, okay? Because you might remember that when we were expressing these complex numbers on our complex plane as vectors, and then we use that to express things like voltages and currents, basically what we're doing is we're removing the time element because it's not the important piece to us. And we're saying we're going to just do our math for the pieces that are important. But if you put the time element back in, these vectors that I'm showing right here actually do produce waves. And I want to show you what that looks like for this problem. Okay? I had to rotate it a little bit because what we're trying to do is get the real component, and I'm trying to plot that on this horizontal time axis. So you'll see the piece that I just showed you there. I took these two graphs and I rotated them 90 degrees, right? So there they are sitting there. How we solved the problem, that's what they are. But this is what we leave out. This is the part we intentionally remove because it's added complication that's not the most important part of our problem. It's that those are actually rotating vectors. And this is what that looks like. So what we just solved is that we now know the shape of these waves for those different voltage and current values by just doing the complex analysis that we just did. Right? When we come up with what those complex numbers are that are represented by vectors, what those represent are these time-based waves, and you know, we can essentially, if we care to, we can add back in the time element so that we can know what those waves look like. That's what it is when you convert it back to time domain. You now say, okay, let's look and see what happens with the waves. Does that make sense? And when you're talking about phase shifts, what you're talking about is where do the peaks occur for one value relative to another, right? And we get that by essentially understanding these complex numbers as being vectors that rotate, but that we ignore the rotation part of it. Does that kind of make sense? Okay. Someone once asked me whether or not I used MathCAD to generate this, and the answer is yes, I did use MathCAD to generate this animation right here. So, pretty fun stuff. I enjoy that. Any questions? None? Okay. We'll call it good.